This is Sai Vodapalli. Today I'll be presenting you my understanding of the solution for assignment 7. So in assignment 7, we're going to implement, we asked to implement autoencoder and variational autoencoder. So we're going to use the autoencoder to the images, like we're going to add denoise the images, like we're going to add noise to the images, and then we're going to implement the autoencoder, train our autoencoder model, and then see if the autoencoder can extract the clean images, like take out the noise and then give out the images. And in the variational autoencoder section, we are gonna use a distribution for the images, and then we try to generate some fake images, images that never have been existed, kind of thing. So getting into the autoencoder section here. So our initial program starts with loading all the libraries that we're gonna need. Like we're gonna need some random, we're gonna generate the random noise. So we're gonna need the random NumPy for and MATLAB, Matplotlib as PLT, TensorFlow, and all the necessary. We're gonna load all the necessary libraries, and also we're gonna load some random seed. And so getting into the code, as we can see here, we imported all the libraries, and then we set the seeds, seeds to 99. That can be anything. So basically, the seed is like the initial point of the random set. So, all right. For the images, we're gonna load the CIFAR10 dataset. So, so to do that, CIFAR10 dataset, when we load the dataset, it gives out the training, testing datasets, and also the training and the testing labels. So here we are loading the X-train, and we are not going to use the labels in this example, in this problem. So we are not loading the labels into any variable. So we are just loading the X-train and the X-test. So that's what we're going to use in the problem. So we loaded the X-train and X-test, and then we just printing out the shapes of the X-train, X-test, see how big the data is and what's the shape it's taking. And then we are just, so what we're gonna do is, usually the CIFAR10 data has like 50,000 training data sets and 10,000 of test data sets. So that's huge for the computational. So we're going to just reduce that data to 15,000 for train samples and 10,000 for testing samples. So one way of doing it is we can use the random.sample from the X-train, which is like 50,000 here, the index. And then we're going to just generate 15,000 random indexes. Okay, and then we are going to use those random indexes to select the random data sets. So here the random.sample, we are saying, okay, from 0 to whatever the 50,000, select 15,000. So it's going to pick 15,000 values from the 50,000. It could be like 1, 10, 10,000, 11,000, or anything between 0 and 50,000. And same thing we're going to do for test here. So from 0 to 10,000, we're going to randomly pick 1,000 numbers. So after doing that, we are giving those numbers as an index to the X-train. So whatever the index, it's going to load into the X-train. So now by that, we're going to get the 15,000 randomly selected data sets, and then 1,000 randomly selected test data sets. So we can we're going to verify it by using the print function here. So as we can see here, initially it was like 50,000 data sets and 10,000 data sets for training and test. And then after randomly selecting, we got like 15,000 data sets for training and 1,000 data sets for the testing. So of course, we're gonna, so next thing, okay, now we got our training and test samples. The next thing we're gonna do is we're gonna normalize our data. So to do that, so CIFAR10 is an image classifier. So it's an image. So each pixel value, again, you have like a 256 value. So we're gonna divide it by 0 to 255. So the maximum value that the pixel can take is 255. So we're gonna divide it by the maximum value. set it as float and then divide it by 255. So that's how we gonna normalize the data. So we to do that again, so we are normalizing the X-train samples and the Y-test sample, X-train and X-test samples data sets. And then we are also specifying the input shape, which is 32 by 32 here. So X-train of 32 and X-train shape of the second index, which is 32 and by 3. So once we set the input shape, then we are going to generate some random noise here. So to generate the random noise, we are using Gaussian noise. So to implement that, we are going to need numpy.random.normal. So as we can see here, we are defining a function to add the random noise. So let's say if I give some input data to the function, so it takes some mean and distribution for the Gaussian distribution and generates the noise according to the Gaussian distribution. So that's where expression in the mean standard, and we want the size to be in the same size as the data set, which is like 32 by 32 by 3. So we are specifying the size to be that. So now we got the noise. Now what we're gonna do is we're gonna clip this noise to our clean or like the input data. So that's how this function is gonna work. So when we send the input data, like a clean image, it's going to generate the random noise and adds to the input image and generates the noisy image. So we define our function here, and then we're going to implement this code to see how our function works. So as we can see here, we are generating all the X-train samples, like the 15,000 data sets that we had, and the X-test, which are like 1,000 X-test samples. We are generating the noise for them. And then or whatever the noise generated files, they're gonna store in noisy X-train and noisy X-test. So just to check, we are implementing the function here. We are using the MATLAB plotlib to see how the actual images are and how the images are after adding the noise. So as we can see, we are showing the X-train, which is the clean image. And then we are showing the noisy train for the same index. So as we could see here, this was the clean image or the actual X-train, and this was the noisy image. And same here, clean image and noisy image. As we could clearly see, like all the images, all the images with the function that we defined, there was some noise added to the images, and we got the noisy image samples. So now we're gonna develop the model autoencoder. So we're gonna, half part of the code will be the encoding part, and the other half of the coding will be the decoding part. So we're gonna define the structure here. So as specified, we're gonna define the layers as specified. So as you can see, the convolution layer it has 28 filters, size 3 by 3, and activation function as value. And then we are implementing the maximum pooling layer, which extracts the maximum value. So here we said 2 by 2, so which is like a 2 by 2 matrix. So it takes the maximum value off from the 4 values. And then we are adding the padding same so that the input shape doesn't change. So as we can see, then we are adding another convolution layer and then another maximum pooling layer. So we are specifying the padding same. So padding same does is it tries to maintain the same shape. It maintains the same shape after these layers by adding some synthetic data. So then we also implemented the decoder function. So then based upon all the layers, then once we added all the layers, this is our model. So as we can see, convolution 32, 32, 28, and then after adding padding same, the final shape of the convolution layer is still 32, 32, and 3. If we don't add the padding same here, your input, the final shape of the input image could be different. So as you can see, as we implemented these 7 layers, we got a total of 22,795 parameters to get trained. So here we're gonna compile the model using noisy extrain and extrain. Okay, so why we are just using two extrains here is, okay, our main objective is to clean the images, to clean the noisy images. So our input will be a noisy image and the output will be a clean image. So noisy extrain is the noisy image and extrain is which is our output, or we can call it as labels, is the clean image, or we can call the desired output. So when we are fitting our, so that's why we're fitting our model with, okay, my input is noisy extrain and my output should be the extrain. And we set up the epochs 15 and batch size 256 and the shuffle as true. So it randomly, selects the data. And verbose 2 just shows the extra process, like how the process is going. So after running the model for 15 epochs, we are gonna save the model. So which can be, so once the model is trained, we can save the model with the desired name, and then we can use the model, like load the model in future and test it. So over here, we are saving the model as a my denoiser, excuse me, saving the model as my denoiser. So that saves autoencoder.save as my denoiser. So it's going to save the trained model as my denoiser in the folder. And then we are going to use the load model function to load the model, like assuming this is going to be in future, like when we are going to test the system. So we're going to load the model using load model, my denoiser, and then we're going to test the, we're going to predict the test samples. So here we're going to plot the images based upon, okay, so what exactly the test image is, and what exactly is the noisy image is, and what exactly is the output of the model that we trained. So as you could see here, so we're printing out, like showing the X test and noisy X test and denoised X test. As we can see, so this was the initial clean image of the test sample, and this was the noisy image that was generated using the Gaussian noise. And then once the noise is generated, we are inputting that to our model. And then this is our denoised, like this is our cleaned image by our model. As we can see here, like for different images, it cleaned the noise very well, but there was a bit error in terms of the pixel, but that can be, that can be overcome by using more data sets, or training more and trying to get best accuracy from the model. Then it can give out more cleaner images. So that's how we're gonna use autoencoder to clean the noise out of an image. So now we're gonna use the variable autoencoder concept to generate some fake images, fake digit images that never existed. So again, we're gonna just use the train. We are not worried about the labels in this case, because we're just gonna use the training samples and then train our model, and then try to, based upon those trained samples, we're just gonna generate the fake digits. So we are not worried, we're not gonna care about the labels in this case, in this example. So again, so we're gonna, so that's why we're gonna just load the X train and X test, and then we're gonna reshape the, again, we're gonna reshape the data or reshape the image to 28 by 28 pixels, and then set it as float and divide it by 255. Like I said previously, that's the maximum value of a pixel. So we're gonna divide it by 255 so as to normalize the data. So all the data sets in the X train are normalized here. And then, excuse me, and then here, we're gonna specify the input shape. Here it's a 28 by 28 pixel image. So X train is shape of 1 is 28, X train shape of 2, index 2 is 28 again, comma 1, that would be our intent shape, input shape. And then here we're gonna find the latent dimension as 2. So what exactly it does is whatever the digit it is, or whatever the, let's say a digit of number 3 or something, it reduces it to a two-dimensional vector. We can call it a vector. It has a magnitude, call it as like a magnitude or a direction, like it has two values. So each image is reduced, each digit is reduced to two dimensions. So here we are generating a distribution for all the digits. That was so once all the digits are reduced to two dimensions, then we are gonna use a Gaussian distribution for these generated vectors. So to do that, here we are implementing the we are calling a function. First, we are implementing a layer, Keras layers, and then we are calling a function calling a self and distribution, where the distribution has the mean and variance of the Gaussian distribution that we are gonna the sample Gaussian distribution that we're gonna have. And then as we can see here, the code is provided here, which is sample TF Keras backend random normal. So we are just randomly inputting the normal, means the Gaussian function here, and then the shape to be specified as shape mean of 0, and then TF shape of 1. And then once we calculate the sample here, we're gonna return the mean value that we had plus the exponential of 0.5 of the variance, which is 1/2 of the variance, and then multiplied by the sample. So this adds the mean and distribution. So that's what the output of this function will be. So now we are gonna build a variable autoencoder. So here the layers are defined. I mean, we are given the layers. So again, every autoencoder has an encoding part and the decoding part. And in this case, we're gonna import another model to stitch this encoder and decoder part together. So firstly, we're gonna look at the encoder section here. As we can see here we are implementing the 32 kernel filters with 3x3 size, activation function as ReLU, strides 2, and the encoder input, whatever the input that we had, and then that's the X, and then we're gonna use that X, multiply here with the next convolution layer, and then we're gonna flatten it and then dense. So these are all the layers that were provided, and then we're gonna extract the mean and variance from the dense layer. So here we are latent dimension is 2, and variance or dense of latent dimension. So here it's going to be 2. So we're going to put the mean and variance, and then we are going to send those mean and variance to the function that we define, and from that we're going to get the completed encoder model. So we're going to close the, save the encoder model as encoder, and we're going to keep it aside. Then we're going to work on the decoder. So for the encoder part, like after implementing all the layers, we got a total of 55,764 parameters that needs to be adjusted or trained. And then for the decoder part, these are the layers that was defined, given. So we are starting with the dense layer, and then we are reshaping, and then we are using the convolution 2D transpose, because initially we use the convolution function, and now we are decoding it. So we're going to use the transpose function. So again, we are using the padding function, same here. So as to have the same input shape. So as we can see here, after implementing the decoder, we are saving our model as a decoder with the name decoder. And as you can see, like once we implemented the decoder function, we got like 65,089 parameters that needs to be trained. So now, now we're gonna import, like I said earlier, we're gonna stitch the encoder and decoder together to get our final model. So to do that, we are implementing wget that's gonna get the file from the provided path, As we can see here, it's a zip file. So we are using the unzip function to unzip the function, unzip the file that we extracted. And then this has the file has a custom module, and in the custom module file, we are importing from the custom module, we are importing custom VAE. And from that, we are importing VAE model that's gonna stitch our encoder and decoder together. So as we can see here, VAE equals to VAE of encoder comma decoder. So the new model that stitches the encoder and decoder is stored into the small VAE. So now we're gonna implement a function calling training. So what exactly we are gonna do is based upon the training now. So let's say if I wanna train the model now, and I give the model VAE and say, okay, train my model now, then it's gonna train the model based upon the parameters here. So we are compiling it using the optimizer Adam and setting the epochs to 15, batches to 128, and shuffle as true using the extract samples. But the problem is it's gonna take a lot of time. So we gonna in this case we are asked to use already pre-trained model. So again, like the same function that we used earlier, we're gonna get the file, which is a zip file, and then we're gonna unzip the file, and then we're gonna load the model, which is my trained VAE decoder model, which was trained earlier, like a trained model. So once we load that model, we're gonna use that model to test our samples. So if my train now is true, then it's gonna compile right away. Like it's going to compile the program immediately and then test the samples. If my train now is false, it's going to use the already pre-trained model. So if it's true, it's going to train the model. If it's false, it's going to use the already trained model. So as you can see here, trained VAE encoder, when it said true, it trained the model for 15 epochs. And when it falls, it just loaded the model that was used, like that was previously used. So once we load the model, we just gonna use the model to randomly generate some fake images. So I also okay. So here. Okay, I didn't run it. Okay, so yeah, here we the last step was we are going to reset it to false. So the trained VAE decoder here will load the already loaded parameter, already loaded model. So using that, we are going to generate some fake images. So as we can see here, we are plotting, we are using the plot function to plot the generated images and random latent vector. So again, we are using np.random.random and latent dimension, which is a value of 2. So this will generate two random values here. So and then we're going to use those two random values and use the trained model that we had to generate and see using the Gaussian distribution. We're going to see, okay, these two, where these two values are, like where this vector is going to fall under, and using that, we're going to generate some fake image. So we generated the two values, I mean, like a vector. And then using that vector, using the trained VAE VAE decoder, we're gonna say like predict the function. So using that, we get a fake image, and then we are reshaping the image to 28 by 28 pixel size. And then once we do that, we are just plotting, like we are just looking at the generated fake images. As we could see clearly with the random.rand function, the vector generated like 0.83, 0.53, 0.35. These are the random values that was generated. And based upon these random values and based upon the trained model that we had, it generated some fake images. Like here, it looks mostly like digit 2, digit 3, 3, digit 3, or 3, 2, 3, 3. So all these images which are randomly generated are completely fake images which were never existed. So this is completely it's very fascinating, you know, how the digits, how the model was able to generate some fake images based upon, like, you know, getting trained from the real images, and it's able to generate some fake images. Just about it. Thank you.